Okay, hello everyone, good morning. So I'm Ayu from EuroRacing team. Today with my colleague Michele Verrucchi, we'll talk about our experience in the Indy Autonomous Challenge and giving you an overview of what we did in less in a technical point of view perspective, but more in our experience, what we did in general, what we will do soon, and what are the future collaboration that we can create with other students and other people. I will go ahead through the whole presentation. If you have questions, please collect them. In the end, we'll dedicate a bit of time for the questions. So let's start about talking about the autonomous racing. So the autonomous racing domain is something that started more or less in 2016 with the RoboRace competition and the F110 competition. They were quite two different kind of competition. The F110, it's more an open platform for students and researchers to test and learn the autonomous driving stack in a safe and, let's say, less expensive way. The RoboRace instead is something that was quite more challenging. The goal was to have something like the Formula E competition, but with autonomous race cars. They are equipped with Lidar sensors, radar, GPS, optical sensor, and so on. Then in the 2017, the Formula Student competition introduced a driverless class in which students has to create a vehicle that should be autonomous, and they need to decide about sensors, computing platform, and so on. So then in 2019, the ESN Energy System Network with the Indianapolis Motor Speedway started to think about a new competition, a new international competition in which several universities around the world could participate. And initially, the goal was to have a multi-vehicle competition. Then in November, they set the rules and the format and opened the registration for a $1 million first prize race competition. In order to achieve this goal, they scheduled 5 rounds in which there were different kind of goals, including a simulation race in order to prepare to the final one. It was quite successful since the beginning. A lot of teams registered around all the world, more than 30 universities, 16 teams participated in the final simulation race, and 9 of these 16 accomplished to participate to the real one in the Indianapolis Motor Speedway. So now let's talk more about the track. So for who is not familiar with the oval racing, could seem something quite easy. You see 4 turns, you can say that it's quite simple to drive around it. You should consider that it's a 4-kilometer rectangular oval track with 2 long straightway, 1 kilometer long straightway, in which you can achieve even 300 kilometers per hour. You have 4 banked turns up to 9 degrees of banking, and even if they seem quite similar, all the turns, they are all slightly different. Now let's talk about the vehicle. The organizers set the challenge to be with the same vehicle for all the teams. Dallara USA and Deep Orange worked together to create this car. It's based on the Dallara Indy Light's chassis, so the same chassis used for the Indy Lights competition with the oval aero setup. The engine is different. It's an Honda with 300 horsepower. It's designed, as I said, by Deep Orange, which is a research group from the Clemson universities. Instead, the setup and mechanical adjustments have been done by Juncos Racing. About the electronics, it's equipped with AD-Link with Axion, CPU, RTX Quadro, GPU with 64 GB of RAM, a Cisco switch in which the main goal is to let all the sensor can be let's say interfaced with the computer and with all the other modules. And there's an ECU called new EuroRaptor, which the goal of this this ECU is basically to communicate with the actuation. So it's one of the most important components in order to actuate the steering and the throttle. Then there's the fluid mesh, which is a module, a wireless module that let you communicate with the car wireless. So from the pit you can communicate with the car thanks to this module. Then about the sensors, we have 2 Novatel GPS. Each one has 2 antennas, so for a total of 4 antennas. 3 radars, 1 frontal, 2 on the sides, 3 luminar lidars, and 6 cameras.
Okay, so now let's have just a quick view of autonomous driving for maybe ones that never heard anything about that. So let's just have an overview. So, of course, it was an autonomous race competition, and we had to develop the code for autonomous driving. In general, what you have is you start from the hardware. And the hardware is not just your CPU or your GPU, but it includes also all the electronics, the sensor. So everything that is hardware is on the base. Then you have to start to communicate with the hardware, and especially with the sensor. You have to process all the signals. Maybe from just the cameras, but also the lidars and every sensor that you can think of. You have to handle all of them. And given that you can have more than one sensor, you also want to do some sensor fusion. So you have to synchronize your sensor and to know and to be sure that the data that you're looking at are at the same time. Or do something that is more difficult, more complicated. And then the sensor, some of them are there to tell you what's around you. So you need them to perceive the world and see what is in your environment. But to do that, you need to perform some tasks. For example, object detection and tracking. So you want to detect these objects, but you also want to track them, because you want to recognize that it's the same object in the same, like in very iterations. On top of that, you want to build everything else. For example, once you have a sensor and you handle the data from the sensor, one of the main tasks that you want to do is to localize yourself. So you have a car, you perceive all your sensor, but you also want to know where you are. And this is the task of localization. And generally is coupled with another task that is the mapping. So what's the difference? So the mapping is something that can be done also beforehand. So you map your environment so that you already know where you are, and then you have a map, and then you want to localize it into this map. But in any case, the localization is very important, because, of course, you cannot take a decision without knowing where you are. All these tasks, we can say that they're in the perception group, because they really rely on the data on the sensor. And then there are some tasks that are more in the action group, because now that you have all your data from your sensor, you have to decide what to do and what's your next step. So, for example, you need a planner. So you need to understand what's your next move. For that, generally, there are 2 kinds of planner. A global one that decides your whole mission. So what's your final goal? And then you also need a local planner to take a decision in the near future. And then there are other kind of tasks that are related to all the behavioral decision that the car can take. But all of that, all these tasks just lead to one final task, actually. That is the control. So there is this, let's say, very important task that is the control that takes into account the control of your car, of your vehicle. And as to the side, the things that you have to send to the actuator, that are actually the acceleration, the brake, and the steer. So of course, at the end, the car, you drive the car with just these three values, but all the rest are needed to understand which three values to send to the car. Okay, so this is just a very general overview. And it's a stack that everyone could implement in whatever way. And then we implemented our stack. So EuroRacing Autopilot. But let's start from the sensor. So I told you the first thing is to handle the sensor. So you told already that we have 2 GPS with 2 antennas each. So we have one GPS here and one GPS. One is the primary and one is the secondary. One is more reliable and the other is the secondary. And this GPS, I mean, everyone has a GPS. You have one in your phone. So is it the same? Of course, it's not, because your GPS, yeah, it's the same kind of sensor, but it's not very precise. So your GPS could have an error of 2, 3, 10, 50 meters on the position that is giving. In our case, we had the GPS, but we also had the correction, the RTK correction. So we knew the position of the car, but our precision was around 2-3 centimeters. Okay, so it was very precise. And this sensor was very important, and almost every team, I could say all the team, relied on this sensor to localize the car in the track. Then we had 3 Lidars, and from Luminar, and these are solid-state Lidars. It's a laser scanner sensor. And having 3 of them with a field of view of 120 allowed us to cover the whole car. Also, Ayub already told you, but we didn't decide anything about the sensor, about how to position them. It was already decided by the organizers. Then we have the cameras. We have 6 of them. Sorry, Ayub. We have 6 of them, and they're slightly different. So we have 4 that are the same, with the same field of view that cover the whole car, and then we have 2 additional ones in the front with a smaller field of view. They are all RGB cameras, and they run at 12 kHz. And finally, we have the radars. Ayub told you that we actually had 3 radars in the car, but we decided to use only one. That was the one in the front. And the radar in itself had 2 kinds of field of view. One that is larger for closest object, and one is smaller to see farther. And this one as well this one was running at 10 Hz. And here you can see the whole overview of all the sensors. So how the car was completely covered. The car was completely covered. But let's start from how we handled those sensors. Okay. So let's start from the cameras. On the cameras, we decided to perform object detection with a neural network. So what we did was to take YOLO V4, that is a neural network, very famous because of its real-time performance. And what we did, we retrained it to detect Formula 1 cars, because of course they're not as urban cars, they're the cars that we see every day. So we retrained it, and we optimize it on our internal framework that is called TKDNN. On that, we also performed distance estimation to see how far the car is, and that was based only on geometrical information of our lenses. And of course, we also implemented object tracking to be sure that we recognize that the car that we detected was the same also the next iteration. The problem with that, you can see that we achieved only 10 frames per second on the GPU for 6 stream. Why I said only? Because we expected our performance to be higher, but the point is that Ayub told you that we had GPU that was the RTX 8000. That is a very good GPU, but for training, not for inference. So it wasn't the best one for inference, and in the end, we decided to use only 4 cameras. One good point of the camera is that the camera can see very far away, like almost 200 meters. Then we had the Lidars, and of course, we used also them to perceive the world around us. And on top of that, we performed clustering. We decided to perform 2D clustering, and we also implemented the tracking. So you can see that the box that we can detect is always the same because it is the same color. And this was actually very fast, the execution, even though it was on the CPU. But the problem of the LiDAR is that the range in which we can see is very small, only 60 meters. But it is very reliable. So when we see something from the LiDAR, we are very confident with that information. Finally, we have the radar. And the radar, I don't know if you can see it. So we have the red points that are the ones that are static objects, and then in yellow we have the ones that are the moving ones. So we knew from the radar which objects were static and which moving. But the nice thing from the radar is that you already have the tracking and the estimation of the speed of the vehicle. And the other very nice thing is that the range, again, is over 100 meters. So here, just to let you know that, yeah, you have to process all that information, but then you also have to put them all together, and also from the same point of view. So you see that the sensor were in different position. We had to construct, let's say, a system like a reference system in which we knew where our car was and what the car saw, and reproject the objects in the correct location. And here, you can see here our car. This is driving on the race line, and I'm sorry, it's quite bad. You can see the LiDAR and the radar together, and then all the objects that are outside the track that were not considered.
Okay, now so let's talk about the planning. For the planning task, as Michaela said before, we have basically two different parts. So the global planner and the local planner. For the global one, we do offline race line optimization using a solution in which we highly base our results on the model of the car. We have a simplified 4 wheels model, considering the tires, the engine, the aerodynamics, and other components. The goal of this task is basically to generate a race line which minimizes the lap time, but not just this. There are several other things that should be considered. Like the track banking, as I said, the track has a 9 degrees banking on the turns, which makes the dynamics of the car a bit different. Indeed, there are even in the dynamics camber effects on the car, but also it's trying to minimize the rate of change of the inputs. So do not, in order to not accelerate and decelerate too quickly, or having a smoother steering wheel angle. In order to do this optimization, we don't use the classical Cartesian coordinates, but curvilinear coordinates, in which there are 2 components, the longitudinal and lateral one, which are referenced to a unique race line. So each race line has a longitudinal progress component and a lateral offset. So the good thing about our global planner, so our optimization is the fact that it's highly based on the model. Indeed, you can see here two different race lines generated from the same algorithm. The red one is a more classical race line. You can see this is the beginning of the main straight, so after the turn 4. The red one try to keep the right part of the track. Instead, the green one is generated considering more the steering rate of change. So trying to minimize the rate of change of the steering. This effect so that it's exit more smoothly and going more outside and then smoothly going inside on the center of the track is due to several reasons, but mainly on the fact that the rate of change of the steering wheel will be less, and also due to the camber and other dynamics of the car. This is something that makes a lot of difference in the signal that outputs the car, let's say the smoothness of the car, of the final behavior of the car. Let's talk now about local planning. So once we have our reference line, we need then to avoid obstacles and collisions, so opponents and static obstacles. For this task, we use the Frenet-based planner, in which the goal is to generate optimal trajectories. And basically, the thing is that we use quintic polynomial due to the fact that they help to minimize the derivatives of the accelerations. And starting from the original algorithm, we added some soft and hard constraint for collision avoidance. And also decided a new cost in order to decide in which part of the track we need to overtake. This is one of the main differences respect other classical solutions. And also we try to set the solution in a way that it's easily in which it's quite easy to change costs in order to do a more smooth lateral change, or maybe to merge to the reference in a quick way. So this is let's say an example from our visualization in which the yellow line is the one generated from the planner, and the blue one is the virtual obstacle moving opponent. It works quite good, as we'll show you also in real footage, both for static and dynamic obstacles, even if you should consider, but I will talk more about this later, you should consider that in this simulations we don't have the perception part simulated in a really high accurate way. So now, let's see how it behaves in the real world. First, using in static objects, which is, let's say, a scenario in which the planner works really great. In the first one on the left, let's see first. In the first one that you saw now, it was overtaking those two pylons, which was also a component of the race after the single time trial. It was working quite good at 120 kilometers per hour, which is, I think, one of the highest speeds that during the whole competition the teams could achieve overtaking these static obstacles. In the second one, instead, we use some more classical boxes and trying to overtake on the turns. Let's see if you can see it. Yeah, and it was quite smooth and fast in this scenario too. Then now the case with moving objects. So with another car. This is the, let's say, the most challenging part of the whole competition. Indeed, as some of you already know, in the end, there wasn't a multi-vehicle competition due to the fact that there were really a short amount of time for testing, but also because the level and the challenge was quite difficult. In our case, the planner was able to overtake other opponents. We tested with other teams, even if with a lesser performance respect the static obstacles. Okay, so now let's talk about the other two modules that just to be brief, I gathered in the same module, which is the supervisor and failure detection module. These two parts are quite important. Maybe one of the two of, let's say, most important parts, in my opinion, which are not related to directly like algorithms and some heuristics, but more, let's say, behavioral commands to the car. So, for example, the supervisor's goal is to control and manage the race control. So the race control flags, which can, for example, you can send the signals to enter to the pit, to exit to the pit, to stop the car, and this can be done also for safety reasons. So, for example, for a race control people, so not directly your team, and also to control and manage the communication between some modules. The safety layer part basically try to detect failures, so even software side or hardware side, and then try to send some signals and change the behavior in considering these failures. So now let's talk about the vehicle dynamics. We could, let's say, talk about this really a lot for a long time. I will try to be short. So the vehicle dynamics division of our team, I think that is maybe the part in which we focused more respect the other teams in the competition, and the guys who worked on this part, the goal for them was basically to measure and try and find the dynamics effects of the car. So basically to understand, estimate the engine force, for example, the camber effects, the tire forces, the differential slip effects, aerodynamics, and so on. So, for example, to focus on a part in which was quite important for this challenge, the tire model, we based the model on the Pacejka magic formula. For who doesn't know this, it's as you can imagine from the name, magic formula is not a proper, let's say, a physics model of the tires, but it's just a model in which using 4 or 5 or even more, considering the different kind of formula. You have 4 or 5 coefficients. In this case, in the formulas, you can see B, C, D, and E. Those coefficients that can then fit some data of the tires. Usually the data are collected from using the slip angle versus the forces, the lateral or longitudinal forces, and then you have to fit this data with your model. The data that we gathered basically was from the Bridgestone tier file, so files in which there are already some coefficients, but from the tires, let's say, tested in a static environment, so not directly on a car, on a road, doing some particular maneuvers. So it was a good starting point, but not exactly what is, let's say, is going on the car. So in order to try to simulate this, we use some multi-body model simulation, which we will talk more in details soon. And then collected some real data on track with different conditions. Another thing to add on this is that more or less what you can see here, so those formulations are really the basics of this formula, but then we added with the collaboration of Megaride, a startup from the University of Napoli, some other parts that can consider some other effects, particular effects of the car. So here, as you can see, there are the waving maneuver. So in order to warm up the tires, we've done like waving maneuvers. Basically, this can be done in two ways, just to be short. One is in an open loop way, which could seem quite, let's say, dangerous, but honestly, it works quite good. Or in a closed loop using creating some sinusoids to be tracked by the controller. This is something that was quite important in order to create heat on the front tires, even before going too fast, because you can hit the tires going faster, so even 200 or more, and maintain a certain speed, but this can create some dangerous, since the front tires that gives the directionality of the car are quite cold. So now let's talk about the control part of our stack. We basically use a model predictive control for higher speeds and let's say performance lap times. As for who doesn't know, the model predictive control is an algorithm that is used in several years for industrial topics, but in the last 10 years, more or less, has been used a lot even in the autonomous driving due to the fact that we have higher computers that have higher performances. It's based on a model, so basically the behavior, let's say the algorithm is that you have a plant, in this case is the vehicle, in which you have some inputs, steering angle, throttle brake, and the state of the vehicle. In our case, the position, X, Y, heading, the speeds, so longitudinal and lateral velocities, and the yaw rate. Then we have a model of the car. In this case, is a single track model. I will give you some more details soon. And using this information, so the state and the model, you can predict the future states. And in this way, using also a reference, that in our case is a local trajectory, so path, velocity, and other references, you can check the future errors, the algorithm check the future errors, and having a solver can understand what are the best inputs to give to the car for the next steps. For the solver, it's important to set some cost functions and constraints. Basically, for the constraints, we use more, let's say, the main ones are the speed, throttle, brake, steering wheel angle. For the cost function, we had several ones, soft, more, which have more or less weight. So, for example, the velocity and path tracking. So, in order to give more importance to tracking the path or the velocity, the progression, inputs, rate of change, and so on. For the solver, we use the HPPM, which is an interior point method, but optimized to be used in real-time applications. So as I said, we used a bicycle model for the model predictive control. The reason for this is that it's quite a simplified and less computational heavy model. This is a really simplified, let's say, version with respect to what we used. But basically, yeah, we have 6 states in which we can predict, let's say, generate the next steps using the past inputs, but also calculating the forces, the front, rear forces, lateral, longitudinal, and having some information, some cost, static and dynamic parameters like the mass of the weight of the vehicle, the inertia, and so on. So, as some differences respect the other model that we used is that is not in Cartesian coordinates, but in curvilinear coordinates, similar to what we did in the offline optimization to generate the trajectory. This is something that if you want to check maybe more in details in the reference, you can see that having a less difference between the offline optimizer, so the global planner, and then the control, so the way in which you generate the trajectory, and the model and the way that you use to control the car, it gives you more, let's say, less tracking error, less a more close solution respect to what you expected during the race line generation and optimization. So briefly, some results, basically from a computational headness point of view, it was quite good. Of course, we had a high, let's say, a really huge computer with a big CPU, a really performing CPU, but the execution time was lower than 10 milliseconds. We kept more or less, I think, the frequency fixed at 100 hertz without any particular issue. The horizon length of the prediction was about 50 steps with 50 millisecond each time step. The tracking error was really low at lower speed, and then a maximum, let's say, lateral offset of 40 centimeters from the path tracking. Here I said a lateral offset and not a tracking error, since it's not, let's say, directly a bad behavior. I mean, we let the MPC and the controller has a certain amount of room in order to accomplish to the differences between the model that you have in the MPC, in the controller, and the real car behavior. Because of course you will always have a mismatch between what you have estimated and what it's in the reality. Due to this point, and also other things like the track condition, the temperatures, and so on. Because you can have a model, you can estimate everything, get data, but then in the real world you will have different conditions, and then your controller should be able to behave correctly, even if it's different from what you expected. So in this way, it was, for example, in the finals, was about 40 centimeters of offset, which is a good result because it means that even letting the controller a huge room to work, it wasn't, let's say, going too much distant from the offset. And another consideration to make is that this controller has been tested and validated only 4 times on track, which is something quite insane. If I should be honest if I think about it right now. So for low speeds and emergency maneuvers, so for example, when the MPC fails, even if it didn't fail even one time during real testing, but even in simulation. But in case that MPC fails, so there are other issues, or we need to go at lower speed. So for example, in all our low speed maneuver, we were using this controller. So a pull pursuit, which is an algorithm that it's more, let's say, it's a geometric path tracking algorithm, in which you have a path composed by waypoints, so different points, and starting from your position, you check the next pose in which you want to achieve, considering a value which is called look ahead. This is quite good for low speed, and let's say it's also quite fast, so you can run it at 1 millisecond, 2 milliseconds without any issue. But and it's also, let's say, deterministic. But the issue is at higher speeds, since it's something that it's only geometric. It doesn't contain any model. If you started to go too much, let's say, have a higher lateral offset from the path, so you have a higher tracking error, you will probably lose the car. This is the reason why I said before that those 40 centimeters of the MPC, letting it quite relaxed and free to work on this range was quite a good thing. So letting this kind of controller, for example, all that freedom could bring almost for sure to an accident. So for the simulation, we had several options, different simulators. For the part related to the vehicle dynamics, we have simulator based on Daimola and Clytex libraries. The goal of using this simulator is basically to do some maneuvers that can be done in the real world, like the ramp steer maneuver, and also to replicate some maneuvers at higher speeds or different conditions. And also a thing that was, I think, quite important is that this tool helped us to understand the real dynamics of the car. So some guys, the vehicle dynamics guys of our team, spent like months to model and set the right parameters to the model in order to have high fidelity one. And then it was quite, let's say, useful to understand the dynamics even before having the car in Indianapolis. The issue, before going on, the issue of these kind of simulations is that they are quite heavy and it's not easy to interface with them, so get the inputs, output, and communicate with them. So it's quite difficult to, let's say, run your whole software stack on this. So in order to have a good trade-off, used another simulator, Assetto Corsa, in which we basically exploit the API gathered and sent by the simulator, and then send our commands using a virtual joystick interface. In this kind of simulator, we have in the control and planning part exactly the same software that we have in the car, so even the ROS2 interfaces and everything. But of course, we don't have, let's say, the race control part, the supervisor. There are some parts that lack in this kind of simulator. But it was quite important in order to have something that has a, let's say, dynamics and that can simulate quite close the conditions. So, for example, we had the Indianapolis track. We had the same Indy Light car that we changed a bit in order to have the same engine model and some other parameters. Then, in order to simulate, let's say, the whole stack, so even our supervisor, the communication with the race control, the GPS, for example, which is something that was basically a ground truth from Assetto Corsa. Here we have the GPS also, and we could also, let's say, simulate a higher standard deviation of the GPS, a jump on the GPS, or even sending the race control flags, so to require to enter the pit to stop the car. In addition to that, we were able also to, let's say, test the whole format of the race. So even the number of laps, the warming procedure, the part of the competition which was about the static obstacles, and so on. So in the left side, you can see the simulator. It's a Unity-based simulator. And on the right side, you can see our visualization in which we see all our stack outputs, and also in the part the other part, you can see some outputs that can help us to understand if we received correctly a flag, if there are some errors, for example, from our stack, which kind of errors, if they are important. We have all the information and telemetry of the stack, let's say. Another thing is that, yeah, as you can see, we can send the flags. So the track condition, for example, here we sent a red flag, which means to stop the car, and that simulates basically the same behavior in the race format for the pylons part of the competition, which we had to avoid collision with these static obstacles. And then we'll send like now the green flag, and the car will start, and you will see that we will simulate also the pylons position, so the obstacle position, and we were able to replicate, let's say, to simulate the exact same scenario. So this is the case. You can see that we'll have obstacles in the right part and then on the left side, and that we can basically understand what's it's going on and how it behaves, and if it has everything let's say correct. So from all our code, what you can get for free or what you can learn. Basically, let's start saying that we used a lot of tools. Basically, we programmed everything almost in C++, but you used a lot of tools in simulation for processing, sensor side, control side, and so on. And let's say that we already released in past some parts, some code that had, let's say, a lot of parts that are common with our software stack, like in the controller part or in the perception or simulation, or also our old software stack used in the F110 and so on, which are something that it's not exactly what we used for this race, but you can get some hints about it.
Okay, so Ayub explained you everything as we thought, as we implemented, and also all the simulation part. So of course, before going to test anything on the car, what we did was test it in simulation, so try it in advance. But the point is that, as Ayub already said, simulation and reality are not the same thing. And I mean, of course, something can go wrong, okay? And basically, there are two things that can go wrong. The things that depend on us and the things that do not. So the things that depend on us, we told you, we tested everything on simulation. The policy was that if it wasn't working on simulation, that it wasn't going on the car, okay? So that was a rule, a strict rule. But even though you try on simulation and everything works perfectly in simulation, it doesn't mean it will work perfectly on the real car, okay? So let's see some example. So here we are testing for the first time with the TU1. So we were at Lohr, which was a smaller circuit, a smaller track, in which we had several test days. And here we tried for the first time our planner and perception together, okay? So here you can see there is TU1, and here's the overtake, okay? So nothing bad happened. So we did actually overtake, we overtook Tum, but the point is that it was very close, okay? So it was just 20 centimeters. And of course, it wasn't what we wanted to do. We wanted to safely overtake them. The problem is that your algorithm, you have to tune them correctly. And if on the simulation everything goes well, it doesn't mean that the parameter that you pick in simulation will be the perfect one for reality. Moreover, we have to consider that our perception, like the perception in the real world and what we could simulate, it wasn't, it didn't really match. So the perception in the real world is a bit more difficult. And then what is other things that can happen? Of course, it's autonomous driving, so everything is software. And you know, I mean, if you're programmers, you know what can happen. Okay. So what can happen is that, yeah, you develop software, but you also insert bugs. Of course, like if you ever programmed anything, you know that when you write code, then you're also writing bugs. And that can happen. You can test everything 100 times, but the bug will be there. And you cannot find it until when you can find it. So of course you do 100 million tests and you can try to see all the scenarios before testing on the car, but that can also happen. that was a very bad day for us. So now I'm laughing, but it was very bad that day. And we found that it wasn't just one bug, but it was 3 bugs. Okay, and maybe even now there are bugs. So what you can do is try your best to simulate everything, to test every scenario, but in the end, it can happen. So these are the things that depends on us. But then there are a lot of things that do not depend on us, and that happened. Okay. So first, I want you to know that we actually received the car just at the end of August. So we had the car from the end of August to the day of the race. That was end of October. So we only had 3 months to work on the car, really test on the car, not only on simulation. And we only had kind of 30 days on track. Okay, so in total, we had kind of 30 days on track, not always on the IMS track, that is where we did the race, but also on the other track that is still an oval, but it's different with different banking. It's very quite short, just 1 kilometer or just a bit more than 1 kilometer. And also we had these 30 days that we had to share with other teams. So it wasn't like we had a whole day on the track. And then a lot of things could go wrong. For example, in our case, we couldn't make cameras and LiDAR work together. Not because our software didn't work, it was an hardware problem. So if we used both cameras and LiDAR together, then our LiDAR stopped working. And we couldn't do anything about that. So what we decided to do was to switch off the cameras, because I told you the LiDAR is more reliable. So we trusted more the LiDARs. So we decided to not to use cameras, even though we had the solution implemented. And then, of course, you lose a lot of time due to the problem of other people, but then you also have the infrastructure that is not ready, because we didn't even have the cars, but also the infrastructure wasn't ready. So we lost a lot of time because of the infrastructure. And then if you lose the RTK correction, it's not because the sensor is not working, it's just you're not receiving the correction from the satellites. So you don't have the precise position that I was talking before. So you don't have just 3-4 centimeters of error, but you have maybe 1 meter, 2 meters. You cannot drive your car at high speed with that. So if we didn't have the RTK correction, not only us, everyone, just we couldn't run. And then something that very bad happened just 2 days before the race. So we had a problem with the sensor and with the GPS. So after one test, we couldn't receive anything. So I told you, you could have problem with the RTK connection. You could lose the connection, the correction, so just for some seconds. But in that case, we completely lost it. So we tried to understand what was it, and actually it was a problem of the cable. The cable was loose. And again, it's not something that you have to fix it manually, and then you have to attach better the cable. But if you lose it while running, you cannot do it. It's not your fault. It happened. Then there was the turbo that was not properly working. And then there were a lot of other things. For example, we just received the rules the day before the race, the official rules. We received the afternoon before the race. And then all the problems with the weather. So the car weren't waterproof. So the electronics, the sensor weren't waterproof. So if it was raining, then we couldn't run. And another problem that we had is that the race happened when the temperatures were very low. And that I will tell you about that later. And in general, we really had a very short time. So probably you understood that this whole challenge was a bit difficult, but with very short time is more difficult. But let's talk about the race day. Actually, let's talk about the race week. So the day was the 23rd of October, and this was our schedule for the week of the race. So we had test days on Monday, on Thursday, and Friday at IMS. So the track where we had the competition. So I told you about our crash, and actually our crash was just 1 week before the race. So what we did on Monday was just to test everything again and to try to see if everything was working fine. So if we didn't have any bugs anymore. And actually everything was fine. We actually ran our car at 190 kilometers per hour and everything was okay. But that was what we did that day. Other two teams actually tried to hit higher speeds. So I'm talking about Polymove, the team from Milan, and TUM, the team from Germany. That day they tried to they tried and did hit 220 kilometers per hour. But something that they did not expect, no one expected happened. Okay, so the car spinned, so 360 spin. So it didn't crash, so it didn't go through the wall, but it just spinned, and they completely lost the car. So it spinned, and then it just went, and then it was stopped. So what happened? So they were actually running at 220 kilometers per hour, but there were a lot of things that no one was considering, and that everyone should be aware of. So first thing is that the temperature was low. So we had a low temperature. So I'm talking about 6 to 10 degrees. But why is it important? Because of the temperature of the road and of the tires. So the tires need to be warm to run at high speed. Okay? So real pilots told us that if you want to hit 250 or 300 kilometers per hour, then the temperature of your tires should be at least at 55 degrees. And if your tires are not warm enough, then you will spin. I mean, you will lose control of the car, okay? Because you don't have enough grip. You just lose it. It's not the matter of your controller is not working anymore. It's just a thing that you don't have grip, so you lose the control. So the point is that you really need to do the warm up. Okay, you need to try to do your best to increase the temperature of the tires. And in this case, we noticed this team and another team that were a very good team to lose the control of their car due to the weather condition, the temperature of the tires, and also maybe the lacking of, maybe they didn't give enough importance to the warm-up. But in that moment, everyone understood that the warm-up was very important. Okay, so we really needed to warm up the tires in order to run at higher speed. And everyone just get a little bit worried, the organizer or the teams, because that was very important. So that was on Monday. And then the rest of the week, we just have, let's say, developed days. And then on Thursday, we have test days. We went to the track and we tested our code. We tried something new on the controllers. Everything went great until we had the problem I told you before. So we had a problem with the GPS. We understood, we completely lost the GPS, and we understood it wasn't just a problem of our TK connection, but it was a problem of the hardware. So we checked what the problem was, and we understood that the cable was loose. We completely lost the rest of the day of testing. And they also told us that, first, we needed that GPS to work, otherwise we wouldn't be able to go to the race. But if we wanted to check and to fix this, we needed to open the whole car, remove everything that was in the car, the computer, all the sensor, because the GPS was just in the bottom of everything. And this operation required 4 to 5 hours. So we lost also the morning after. But actually the day after, it rained, so everyone lost their track day. So we actually just tested one time after the crash and Alpha Day. And then the organizer decided to allow us to have a small test time before the race because some teams, including us, haven't tried the format of the race neither once. And then there is the race day. So the race day, of course, we had the competition. So the competition was divided in semifinals and finals. The semifinals were supposed to have one lap for warm up, two performance lap. So the winner was the one that had the best average time over two performance lap, one cool down lap, and then a competition on obstacle avoidance. So we had these pylons that I will show you, and we were supposed to overtake these pylons and then to pit. That was the semifinal. And the order of the semifinal is this one. And it was just random, and we got quite lucky because we ended up almost at the end. So all the teams just did the semifinals, and the result was this one. Okay, so the first two teams did very good, and they set the level for the race. And some teams had problems with the GPS, and they had some crashes or just lost the car. And then we did our semifinals, and actually we qualified first. So the semifinals went great, and we qualified first. So the ranking was this one, and that meant that the final order was the opposite. So again, we were starting for the last. It was strategically, it was quite good because we could see what the others team decided to do and did before decided what to do ourselves. So that was the final order. Between the semifinals and the finals, we decided to check the temperature of our tires. Why so? The problem is that we had a sensor on the tires, but we actually had it only the last week. So we didn't add a lot of information about our tires. And but we knew, because of what I show you on what happened on Monday, that the temperature of the tires was very important. And we needed our tires to be in temperature if we wanted to reach high speed. So here you can see a chart. On the top, you have the speed of our car. On the center, you have the temperature of the tires. And on the bottom, you have the variation of the steering and the steering angle. So here you can see that there is the waving, so our waving maneuver, that is for our warm-up. And you can see it also because the variation on the steering angle, it's evident. And actually, our warm-up was quite good because we could warm up the tires from 27 degrees to 37. So it was useful. So we were we were doing something good because the tires were warming up. And then you can see the rest of our semifinals, in which we drove at 211 kilometers per hour. And what we can see is that the temperature was higher and increase with this high speed. And we reach 48 degrees. Another thing that I want you to notice is that if we go at a lower speed, the tires don't warm up anymore. I mean, if we go at, for example, 150, it's not warming up, okay? It's colder. They start to become colder. So what we understood is that driving at more than 200 kilometers per hour is very good for the temperature of our tires. Okay. So
there's the green flag from Spot, ready to go. Just 5.
Okay, so here's the final. The final polymorph starts, but they have, and actually they do very good also in the warm-up because they hit a peak velocity of 250 kilometers per hour, let's say an instant peak velocity, But then they have a problem with the GPS and they lose the car, so they have a very bad crash. And then there is TUM, and they have a very clean run, and everything is good, and they actually do a very good job. And then there is our turn.
5 miles left in the Indy Autonomous Challenge powered by Cisco. EuroRacing trying to knock TUM off the top step. Coming into turn 1, posting straightaway speeds up over 140 miles per hour and keeping those speeds up over 140 through the corners, Rob.
Yeah, they're on it right now. No problems. They're looking great. Got through the short chute, no problem. Off the corner, brought down that long back straightaway.
This could be competing philosophies here. TUM electing to go for the high straightaway speeds, but backing it down for the corners. Much more consistent for EuroRacing with speeds both through the corners and down the straights, hovering right around 142, 143.
Yeah, not really pushing it any higher down the straightaway, but it's these center corner speeds are really high, and this is really it's looking pretty promising for him right now.
The speed to beat, a 135.944. That is a 2-lap average, and the record for an autonomous car on an oval set just a few minutes ago by TUM Autonomous Motorsport. EuroRacing across the yard of bricks. The first lap is complete. It's a 139.009 miles per hour.
Wow.
Okay, so the first lap, we actually did the record, right? 223.76 kilometers per hour. And then...
What in the world has happened here?
Okay, so what happened? So what was the final format? I told you the semi-final format. The final format was 4 warm-up laps, because I told you everyone was aware that the tire temperature was a problem. 2 performance laps and 1 cool down, because everyone was expecting the finals, the team in the finals to run fastest than in the semi-finals. And our strategy was to have a format 4 warm-up laps, 2 waving, so with the waving maneuver, 1 at 200 kph and 1 at 230 kph. It was our target velocity for the performance laps. But I just show you the temperatures after semifinals, and I show you because it's what we did. And after taking a look to those information, we decided to change our strategy. So our last minute strategy was a bit different. So it was just 1 waving, 2 laps of 250 kilometers per hour. But because we noticed that the temperature reached in this way was almost the one that we wanted. And then again, to perform 1 at 230 kph and 2 performance lap at 240. We actually had 1 problem with the turbo. I told you that we had an issue, so the car never reached 230, not because our controller couldn't, but because of this problem with the turbo. So we reached 223 kilometers per hour. But here we also introduced a bug. So we introduced a bug and we miscounted the number of warm-up laps, and we did one lap less. So what we did is that after the first warm-up, the first performance lap, the one that we just saw, we started to cool down. So we started to cool down, and the problem, the rules were that the winner was the one that did the best average performance over 2 laps, and we did 223 the first lap and the 150 for the second lap. So of course, TUM won. They really did great, and we arrived second, and Polymoth third. In any case, we won $100,000 for being the fastest team, because we actually set the record for this race, and it's still the record, the fastest lap in an oval in the world for an autonomous car. But yeah, I can tell you that it was a bit heartbreaking for us. Okay. Okay, to conclude, I told you a lot about cars, but let's talk also about people. So who is EuroRacing? So EuroRacing is a team that formed just almost 1 year ago during the pandemic. And we actually met in person only in Indianapolis. And it's a team that was formed from 4 different universities. One is the University of Modena, the Reggio Emilia. One is the University of Pisa. Then there was ETH Zurich and the Polish Academy of Science in Poland. And here we can see that our group was very heterogeneous. And I think it was also one good thing about us, that we had different skills, different expertise. So you can see that we have robotic engineers, we have control engineers, computer engineers, vehicle engineers, and computer scientists. So we try to represent all Unimore. And I mean, we told you almost everything about the competition and our software and what we did and what we studied to be prepared for this race. Of course, having different curriculums and different backgrounds was very important. And I mean, this challenge, this competition was difficult and was complex and required to have different backgrounds, different skills. And we think it was also, we were almost one of the few teams that gave importance to this, and especially to the vehicle dynamics of the car. That was very important for this kind of race. And so I told you, we represented 4 universities. From the University of Modena, Ayub and I are, of course, from the University of Modena. And we actually are from one lab of the University of Modena, that is the HyperT lab, the High Performance Real-Time Lab. That is a laboratory of the department, the film department. And it's actually from the informatics degree. And it was formed in 2014, and there were just 3 people. And today it's a quite big lab. Given that our university is not that big, this lab is quite big. It's 50, 60 people. And the mission of this lab, it's in its name, let's say, so to put together high performance and real time. So high performance because we want to work on complex and workload-intensive tasks, such as perception planning, neural network, deep learning, all the things that we told you before, like they were computationally expensive. But we want to do it, we also want to do them with latency critical control tasks. We want to do them within deadlines. And that is a bit of the mission of this lab. And the other thing is that we want to do that, but we want not to do them on workstation and big computers, but on top of embedded boards. So very small boards that have limited resources, and the power consumption is also limited, and they're not much expensive, and they're very small. But of course, it's more difficult to do all the things that I told you about on top of that, rather than on a normal computer. And one of the main use case of the HyperT Lab is the automotive. So HyperT Lab really likes cars and different cars also. So we actually started with small cars. So the F-110, I told you in the beginning, in the autonomous racing history, this F-110 car are part of an international competition among universities. It's actually a student project, and you have to compete with other teams, and you have this kind of competition every 6 months. And we as HyperT won 2 of them, and but we're keeping participating to this kind of competition, and actually we're competing with 2 different cars, one that is mounting a GPU and one that is the new one that is mounting an FPGA. Then we have projects with a real urban car, autonomous urban car, that are more related to European projects or national projects. So here you can see the final demo of Hercules. It was some years ago. That is an European project. While here you can see a project that is the MASA, Modena Automotive Smart Area, that is in collaboration with the municipality of Modena, and for which we're still collaborating and we're still working on. Finally, in the race field, we also have a Dallara Formula 3. And here you can see that it's driven by our pilot, Nicola, but is going to be soon autonomous. So we will work to make it autonomous. And here it's in the Autodromo of Modena. So if you like this kind of project, if you like this autonomous driving stuff, maybe you can come and have a chat with us. So of course we're open to students for thesis, for internships, and we know that exams are very important in your career. Of course, university is based on exams, but real project in which you are able to work on the real stuff is something that it's very fun and it's very useful for you because you will learn a lot of stuff and you will touch the real robots and the real cars. So if anyone is interested, we can talk after. And finally, to conclude, what's next for EuroRacing? So actually, it's not over because there will be soon another race. So it will be very soon, the 7th of January, we'll be in Las Vegas and we'll take part the CIS. And the 7th of January, we'll have a second race, multi-vehicle. So it will be a head-to-head, two car at the same time. And it will be at the Las Vegas Motor Speedway. Again, an oval, but a bit different, a D-shaped oval with almost 20 degrees of banking. And the cars are already there waiting for us. So thank you for everything. Thank you for listening. And so if you have any question, of course, feel free to ask me here. Also, like we have a lot of time. We kept almost an hour just for questions. So also online, if anyone has questions. Oh, wait, one moment. I would like to call the team members here. So anyone...
I was not in the slides. Can I come as well?
No.
So here in the room, even if you have a question and you want to speak in Italian, it's not an issue. And from online, we can
I actually don't have a question, so can I?
Go ahead.
You talked about deadlines, right? So it seems that there are many tasks around there is perception, planning, equation, and so on. So what are the typical deadlines that you guys need to meet there? So is there any, I don't know, timing constraints that you also need to comply, or maybe this will come after you fix all the algorithm and everything else?
So actually, we didn't have actual deadlines, but all, let's say, our nodes, the nodes of our software, were running at a certain rate. So, for example, I don't know, something was running at Hertz, 20 Hertz, and so on. So, in this case, it's not really a deadline, but we expect the code to respect that. And of course, if we miss an iteration, it's not the best thing. So that was mainly, let's say, deadline, but it wasn't a real deadline. The other thing that we could could do, but we didn't, was to also divide the load of the different cores. So actually, some guys looked into that. So we have 16 cores on the AD-Link, and everything was running on all the CPUs. What was good to do, and we set that up, but we didn't use in the end, was to split the nodes due to, in base of the importance, in order to have, for example, a whole core for the controller, a whole core for the planner. What we did was just to set the priorities. So we gave higher priorities to these tasks that were very important. But next, one of the future works is to split also the load in order to have a dedicated resource for critical tasks.
We have a question.
Yes.
Yes. Sorry, can you hear me?
Yes. Please
Perfect.
go ahead.
Thank you. Yes, I'm really curious about internships positions in this subject, and how does it work? I mean, the application process. Do you have a deadline coming, or?
Not really. Yeah, the question was, what about internship? Do you have deadlines? What's the procedure to have an internship with us?
Exactly.
So you can actually check on our website. It's just ipad.unimore.it. I can write it also on the chat.
Yes, please. Sorry, go on.
And you can check there if there is, let's say, an available subject for the thesis. Otherwise, you can just write to the contacts and write to us. We don't have deadlines. You just have to contact one of us, and we'll see how to do.
Perfect. Thank you. Thank you very much.
That's another one.
Okay, there is another one from
Hi.
Turkey. Okay, hi.
Do you hear? Yeah, I believe you hear me. So this is Tahir from Ford, Turkey. So I'm also an autonomous engineer on Ford. I was just surfing on internet, LinkedIn, and I just saw your presentation invitation. So I just first want to tell you, really admire your effort, and I just want to tell you that it was an amazing presentation. I saw lots of common points that we faced on industry, so such as we are also using Novatel GNSS units, and also we had lots of GPS mislocation issues, and also like cable losing, etc. And I really understand your point there. So I have one question, maybe two.
Yeah.
One is what is the GPU processor that you are using, and also the second that might be very already informed, but I missed probably. The all teams, the 9 teams, they were using the same hardware, or you choose by yourself? So how is it? Is there any rule about choosing the equipment, etc.?
No, so it was fixed. So each team had the same hardware. So the car was the same and the electronics was the same. It was just a competition on the software. For the rest, everything was the same. We couldn't move anything. Even just like moving a camera was not possible. So all the hardware was the same for everyone.
I see.
We use additional sensor, but only for tests. But during the race, everything was supposed to be the same. Like was the same, not was supposed to. And the other question was about the GPU. Like you want, did you want to know the model?
Yeah, for example, I can tell you that we are using NVIDIA products, and I think that's quite common. So how?
It's a Quadro
yours?
RTX 8000.
Okay, that's cool.
And again, it wasn't the one that we didn't pick it, so it was just there. So as I told before, I mean, it's a very good and expensive GPU. It costs kind of like 5,000 euros, and it has 64 gigas of RAM. But the problem is that it's perfect if you want to train neural network. not if you really want to run and do inference. Indeed, a lot of teams didn't even use it because it was kind of too slow for inference. And also, a lot of teams had problems accessing this GPU, but that's another problem.
Absolutely. By the way, do you collaborate for the European Horizon projects? Like right now, it's a Horizon Europe. So maybe in the future, we might have some collaboration about the autonomous vehicles. I saw your lab on the presentation. It's not only for the Indy cars, it's also for the commercial vehicles, for example, I think.
Sure.
Do you open for that, such collaborations like Horizon projects, European funded?
Yeah,
because...
we actually do. We absolutely do that.
Okay, perfect. I think I can contact you on LinkedIn because I have your team web page, LinkedIn page already in my contact list. Congrats again. Wish you best from Turkey. Be safe.
Thank you very much.
Another question from here, even if in Italian, it's fine. Even if you have, let's say, curiosity or minor things.
And the question I know the answer for my students here at the Embedded Systems course, just to pretend that we want to teach is useful. So my question is, among the various tracks or processes that you guys have, how do you synchronize and how do you communicate? What kind of mechanism do you use for communication there?
Do you want to answer? Andrea?
No,
Andrea.
Andrea or Francesco?
Andrea or Francesco, come on.
We do actually use ROS2 because the other teams started with ROS2, so a bit of the base software was based on that, so we go with ROS. We actually had a lot of problem because of latency of the ROS framework. But it was good to separate all the nodes of our software to be isolated and don't create trouble with the other nodes. So, for example, we divide the safety critical nodes like the pursuit, the MPC, and the actuation bridge, and so on, so that if we have a segmentation fault, for example, on one node, it doesn't affect the other.
And the inter-thread communication, do you also use some kind of condition variables, semaphores, and so on, besides ROS?
Sometimes.
Pretend to say yes.
When is needed, we use it. When it's not needed, we don't use it.
Another thing that to add to what Francesco said, and I think it's quite important because it's the thing that helped us a lot in the beginning to not have issues that other teams had, is the fact that in our stack, so the perceptions guys, in particular Francesco, not use directly not directly interface with the sensors using ROS, so the ROS2 drivers, but directly develop our own drivers interfaces. So we get directly data from the sensor, UDP, TCP data, and get them, understand what we want to collect, and then generate the ROS2 interfaces for just what we needed. This was important because there were a lot of issues with the ROS drivers for GPS in the beginning, for the Lidar and other things that helped us a lot. And I think that also considering the real-time part, of this, it was something quite important.
Just one question on the sensors. So, do you use also an hardware or a low-level synchronization mechanism for the sensor?
Yeah, actually, the switch, we had a Cisco switch, a very big switch in which you can connect a lot of Ethernet connection, and all the sensor was Ethernet, so all connected to the switch and synchronized with PTP, which is an Ethernet synchronization protocol. So your sensor need to be compatible with PTP. Or actually, the Novatel, the GPS was not compatible, so it was the only sensor not synchronized.
So the clock was coming from
The switch.
the switch.
Yeah.
Directly from. Okay.
I have two questions. The first one is more related to the system. The second one is related to the simulation. So first one is the system. So you said that basically the only thing that you did on the system was to prioritize some nodes with respect to the other. So you talked a lot about real time and everything. So did you did you have how much let's say were you able to change something on the system installed on the hardware, or you were simply locked on the software? Did you have the possibility to change the kernel of the system, to tweak a little bit the system, just to have more performance from a very, let's say, big CPU that you have? I don't know, did you have the possibility to maybe change the kernel and use a real-time version of Linux so that you can prioritize specifically some tasks? So, yeah, in a better way than a standard Linux. This is the first question.
We could everything that is software we could do it. The issue was the time, because doing that things require a lot of time, and at times that lock the car. So if someone worked on that, we couldn't work on the car. So it's something that we haven't done, but it could be possible.
Okay, and the second question is for the simulation. So you said that basically the weather, maybe the rain, was a problem for the hardware actually that was not was not protected. Okay, but was it the only problem? I mean, if there was actually the rain, and let's assume that the hardware was protected, would the car be able to run, or there were no such a scenario? Even in the simulation, this is why I talked about simulation. So, did you guys simulate even weather conditions or not?
No.
For the race, we didn't do it. So we are working on that. Now we are focusing more on changing the conditions, so having a more slippery track and so on. About the car is, I mean, the Indy cars, the Indy Light car, they officially don't run on wet tracks. Also because you can mount let's say the rain tires, but the configuration in which they are configured, set up, is not properly made for the rain. But even the trucks, the vacuum trucks, are not made for rain. Yeah.
How do you implement the telemetry part? I mean, used which kind of connectivity used? 4G.
It was a proprietary software of Cisco. It's a fluid mesh is called, or in the new acronym is called CURV, CURVW. And it's a proprietary algorithm infrastructure architecture with a lot of antennas around the track. And on top of CURV, we implemented a simple UDP protocol to receive the telemetry from the car. So from the car, we just send the UDP package, and then to communicate with the car, we simply SSH into the DPC. So that's it.
This is for the, let's say, online part, but then offline we can have also other telemetry. like the engine telemetry and other parts that are, let's say, managed with other units, other ECUs.
Did you use the radio signals to reach?
Yeah, we had
Right.
yeah, for example, for the race control, so to control with sending the flags to stop the car in case of emergency, we had ECU called MyLabs, then we had the low-level ECU for the engine from Motec.
Basically, there was two types of connection.
Yeah.
One that we can use it to communicate with the car, and one that the race control use it to send command to the car.
Yeah.
The second one, MyLabs, the one Ayub was talking about, was a radio signal.
Yeah. And it's something that it's used also for real racing, I think, not only for our cases. So for lap timing, GPS, and other things.
And also canvas.
Yeah, and also to communicate directly through the canvas. So for the engine, the actuators, the throttle, and so on.
Okay, we have another question online. Alessandro.
Ciao Michela, ciao Ayub. I think it was quite related to the question that I heard now. My question was related to the fact that did you have access at real time about information about the temperature of the wheel, or, for example, like downforce? So something like that can be used to do like a dynamic planning of the speeds or the trajectories.
Yes and no. Let's say that we had data like the tire temperature, the tire pressure, the some sensor about the potentiometer. So let's say the load on each wheel, something like that, but not so let's say so accurate in order to do a real, let's say, real-time dynamic state estimation about all these things. So yeah, we had some information, but some of them, so for the forces, the tire forces, or the as you said, the downforce, they weren't enough to do something accurate. But yeah, at least for the tires, it was, and the wheel speed, the sensors were good enough to be used for odometry or just telemetry.
Thank you so much. Thank you.
I have a question on the solid-state lidars that you use. Does these lidars have a cycle, or it's dark? I mean, with the normal lidars, we have a 100 Hertz cycle or GHz cycle. 10 Hertz cycle. But with those solid-state lidars, it's the same.
You can think about these lidars about a point that go up and down, and you can configure this point in different patterns. So you have up and down like this, and then you can select a Gaussian distribution of the lines or uniform distribution, and you can change the frequency. You have a lot of configuration about this lidar, and it's pretty good. Yeah, it's 30. Yeah. Obviously, if you increase the frame rate, you will decrease the points because you have less points, but with a bigger frame rate.
Okay, so if there are
no other questions, we're done. And if you have any offline question and you want to discuss further, just in private, you have our contacts, and you can actually find us on Instagram, on LinkedIn, and also on YouTube. So thank you very much for attending today.